So now we'll be discussing about next topic. Okay, so same topic basically, sequential data. So okay, let's start with the presentation. Sequential data. What did we discuss? What approaches we have seen so far to model sequential data? If I give you a sequential data and you want to do anything, classification or uh, I think classification is something which we have seen very nicely. Regression means you want to predict next value or something. How do you do that? How do you deal with what approaches you have seen? Let's stick to the classification problem. How do you do classification for time series? Huh? CNNs? Okay. What else? HMMs? Very good. Thank you. What else? Okay, so I'll reveal the secret. The first method which we saw was template matching. Template matching means I say Hari, I give you my recording, I say this is Hari. And whenever somebody speaks Hari, you match that with this. And whenever it matches, the match is above a threshold, you say, yes, I found a Hari. Right? Just by template matching. You don't have all the variations of Hari, but just I gave you a few recordings, like my speech of Hari. So it's called template matching. Then you saw HMMs. Then we did not discuss it in this context, but yes, CNNs can be used as well. Let us look at these approaches. A quick recap on these approaches and also some analysis. Template matching. What are the pros and cons? Pros means what are the advantages, cons means what are the disadvantages. The advantages of template matching is it's very quick. No need of training, I just give you some utterances. Okay, take a Hari, maybe Dheeraj will give one utterance of Hari, Kavya will give one utterance of Hari, and you got 3 utterances of Hari from, let's say, different genders, from different age groups, and then you are done. Anybody speaks Hari, you immediately match it with this template and you say, okay, whether it is Hari or Kamala or Rama, you have a few options and you can quickly build your classification system without any training. It is very popular. It is popular for tasks which are not very conventional. For ASR, of course not, but for other tasks, many tasks, it is very popular. Okay, I think I gave an example of Duolingo in the class. It is very popular there. Cons, what are the disadvantages? So, how do you find what are the optimal templates? You just got some templates from different age groups and all, but how do you find what are the optimal templates? So, there is no way to do that. It is not much robust to variations in data, right? If I am saying Hari and somebody else comes, he says Hari, it does not match very well. For some weird reasons, you can never improve your model, right? You cannot do anything about it. It just does not match. And people have, actually template matching is also used for image classification. It can be used, right? And when it fails miserably, it fails unexpectedly, and then you cannot do anything about it. It just fails. So that is the problem with template matching. Not much robust to variations in data. And then computationally it is very inefficient, right? The same utterance you have to match with each and every of these templates and it's very inefficient. Next is HMMs. What are the advantages and disadvantages? What is the advantage of using HMM? Let us say as compared to template matching. It is more robust to variations because it is modeling the probabilities from a large training data. So it will learn many more variations, right? Okay. It is easy to train and computationally manageable, which means, okay, it is very robust to, I think I can add this point. Or I can say more robust as compared to template matching. easy to train, and computationally it is very manageable. It has very nice structure, right? And the training is very easy. You can derive all the rules explicitly, no need of backpropagation or something. Yes, EM algorithm is also iterative, but still it is faster, much faster than backpropagation or gradient descent. Um, it can amalgamate easily with powerful models for Px given z. Now, this we'll deliberate a little on this point. Earlier, you saw P of z given previous z. You can store it as a matrix, right? Simply a matrix will do your job. So there, no problem. But P of x given z, how do you model that? So here you can use anything. You can use Gaussian mixture models, you can use simple Gaussians, any other distribution. You can even use deep neural networks. Anything you want to use, you can use there. And that is what brings in a lot of strength. So your models are manageable, very nicely structured, and on top of it, you can use deep learning so easily. So that is why HMMs are very popular, even today, very popular. So most speech recognition tools, they are built on HMMs. But there is a now research is going on to take it further, basically to remove HMMs and make it more. It's called end-to-end learning, where you just learn everything in the neural network itself. Even the transitions are modeled inside the network only. They are not modeled using external HMM. I will tell you what is the reason for that. Okay, so that is so HMMs were a kind of, they came into speech recognition in about 1970s or 80s. I don't remember, 70s or 80s, right? From that time on, even after deep learning has come today, almost 2020, still HMMs are most popular. It is remarkable. It has survived so long. On the other hand, everything else like had a phase. Like neural networks came in the beginning, they faded away. Then again, they rose to glory. And then similarly, we have SVMs. They became very popular in the middle, and then now nobody talks about SVMs. So everything has its own lifetime. Deep learning will also have its own lifetime. You will see something different very soon, probably. Now, the disadvantages of HMM. So this is one major disadvantage which scientists want to get rid of, but they have not been able to do it very efficiently as of now. Self-transition probability decays exponentially. If I'm going from, let us say, first state, again first state, again first state, again first state, so the overall distribution, overall probability is decaying exponentially. It cannot model time durations. For example, when I speak when I say hurry, let us say it is covering 10 frames. And that is the most general, let us say all of us in the classroom, whoever we are speaking and giving our data, we all have approximately our A duration is, let's say 10 frames. 10 frames means 10 into 10 milliseconds, which is about 100 milliseconds. I'm just approximating, I don't know if this is correct or not. Let us say it is 100 milliseconds for almost all of us. But HMMs will always model that distribution as an exponential distribution. You can never model it like a Gaussian with a peak on 10 frames or a Poisson distribution with a peak on 10 frames. It can never do that, right? So the distribution is limited to only exponentially decaying, but it can never become any other distribution. That is the disadvantage of using HMMs. And why is this so? Because of the first order Markov assumption. Because you have assumed first order Markov property, that is why you cannot model that my duration is 10 seconds in general. Okay, this is the major disadvantage of using HMMs. As far as I remember. There might be others. Actually, I made all these points just from memory. I didn't consult any book. I don't know if, where can I find these points. They are all based on my experience. So if there are any discrepancies, so you can ask me. Okay, next, CNNs. Yes, you can also model temporal data using CNNs. How? Yeah, spectrogram or temperatures, whatever. You can consider it as, let's say, you can convolve only in single direction, right? Instead of like in images, you convolve in two dimensions, but here you can convolve in single dimension, and that will be your temporal model. That is the temporal direction, right? In this way, let us say I have said hurry. Let's say this is her, from here to here. From here to here it is ra. Okay, I missed a. Let us say we have a somewhere here. Right? So, how will I use a CNN? I can make a window. This is my kernel, CNN kernel, right? And this will move over the entire audio. I can consider a time series, or I can the waveform, or I can consider the spectrograms as you suggested. And in that case, it will be just a matrix like this, right? But your kernel will be something like this. Means you are just moving in this direction. So this is, if this is n, this is also n. Right? So you are moving just in one direction, not in two directions. Okay. What is the advantage of CNN? Shared parameters. Because same kernel is, let us say this kernel is looking for her and it is finding her everywhere. So there is the temporal shift property, if you remember. Temporal shift is not hindering your match in CNNs. So that is why, because of sharing of parameters, the same kernel is operating over the entire image or sequence. It becomes easy to train. And then computations are parallelizable. How? Because you're just multiplying everything independently. Let's say if you have a very long sequence, you want to run your CNN, so each multiplication you can do independently, right? You can do independently all the computations. So that is why you can parallelize them and it becomes very fast. Actually, if you run CNNs on GPUs, it's very fast. The gains which you get are enormous. Now, what are the disadvantages of using CNNs? Okay. Anybody can think of some disadvantages? One is a finite context length. It cannot handle long-term dependencies. We saw in HMMs, if you remember, our first order Markov property is only on the Z sequence. But the X sequence is not it is not independent of every X before. Right? We discussed it at length in the last class. So, but in CNNs, we have finite context length, so it cannot handle long-term dependencies, right? Because your kernel is of finite length. Next is computationally inefficient. Why inefficient? Because you are scanning with a lot of overlap. You are scanning the time series with a lot of overlap, and which means you are computing so many times over the same input. Right? Hop. Yeah. You can, even after doing hop, it is computationally inefficient. CNNs. If you remember from your images, hop is just how many, like hop size is 2 or 3. Stride, we call it there. Stride is 3 or 5. Or kernel length. Okay. Generally we keep stride as 2, 3, something like that. Still, it is very inefficient, right? Okay. It cannot handle time stretching effectively. If I'm saying hurry, let us say, and my is very long, and my kernel is trying to model her and together, co-articulation. It cannot model it, right? Because has suddenly become very long. So it cannot handle time stretching very effectively. Okay. So that's why we move to another model of neural networks called recurrent neural networks. They are very efficient for time series modeling. What is a recurrent neural network? So basically, what is this? This is a simple neural network. You have an input X. So in this case, I have represented the variables with the circles, and the operations are implicit in the arrows. You multiply the x with w and you do some nonlinearity, you get an h. You multiply h with some other w, you do some nonlinearity, you get y. Right? This is your ordinary neural network. And here, if you introduce the notion of time, so your input is dependent only on this time instant. Or sorry, your input is at time t, hidden is also at time t, and y is also at time t. So your y does not depend on xt minus 1, right? Is this point clear? Your y at time t does not depend on x at time t minus 1. So here comes the role of recurrent neural network. You want to make your y at time t to depend on x at time t as well as t minus 1, and if possible t minus 2, t minus 3, so on. Can you do that? So the answer is, if you can use a recurrent function, or have I written it here? Okay, maybe this will give you a clear idea. So okay, in ordinary neural network you have xt minus 2, it gives rise to ht minus 2, it gives rise to yt minus 2. At next time instant you have xt minus 1, it gives rise to ht minus 1, which gives rise to yt minus 1. There is no dependency across time, right? If you want to introduce dependency across time, what will you do? You just add these connections, right? That is the most logical thing to do, isn't it? Just add connections across time and you get dependency across time. So now your yt is dependent on xt minus 1 via this path. It depends on xt minus 1 via this path. It depends on xt minus 2 via this path, right? So this is so I have unrolled the network in time, right? I have my time t, but I have unrolled it in time t minus 1, t minus 2, and so on. But if I want to represent it only in terms of t, then I can do something like this. I can say my ht depends on ht minus 1 as well. If I have this time delay element. You've all studied this, right? Block diagrams and z to the power minus 1, right? In discrete time systems. So basically this is a time delay element, so that your equation is that your ht is dependent on xt as well as ht minus 1, right? That's how you represent it. So there are two representations which we have studied now. One is this representation, which is at time t only, and then next this representation where you unroll over time. Pardon? They are equivalent, yes. So I'm saying two representations of the same thing. Two representations. They are equivalent. Okay, now the equations. In neural networks, you have ht is dependent on u of xt plus b, right? The weights and the bias. And y hat is dependent on some v of ht plus some other bias c, right? In recurrent, what do? In RNNs, you introduce this extra term where ht is also dependent on ht minus 1. That is it. This is your recurrent neural network. It's so simple, right? Okay, I think we can discuss next topic, means further in the next class.